I think you all should recognize our next presenter, who is Larry Putnam Jr. So I'll go ahead and introduce him for everyone, although I think a bunch of you should be fairly familiar. Larry has over 30 years of experience using the Putnam SLIM methodology. He has participated in more than 100 estimation and oversight service engagements and is responsible for product management of the SLIM suite of measurement tools and customer care programs. Since becoming co-CEO and managing partner of products and customer care, Larry has developed a new customer care program that has increased customer satisfaction levels by 50% and increased client license renewals by 46%. Larry is a member of and active participant in numerous measurement and quality organizations and has delivered numerous speeches at conferences on software estimation and measurement and has trained over a 5-year period more than 1,000 software professionals in measurement and estimation and the use of the SLIM suite. So without further ado, I'll let Larry get started.
Great, thank you, Elizabeth. Well, welcome everyone. I have to say I'm really excited about the presentations that I've sat in on today. I thought Dan and Aaron did a really great job this morning of showing us the importance of size and scope to the estimation process. And Christoph and Angelo talked about the challenges that they encountered standing up a global estimation process in a large organization and across multiple geographies and how they addressed those challenges. And then, Lenny's, I won't even call it a presentation, I'll call it more of a spirited discussion I thought was fantastic on how, they introduced new estimation processes, how they, dealt with some of the challenges of moving responsibilities around among the different stakeholders, and how they got to a more defensible and consistent estimating processes and products. And then Joe just took us over to the other side of the house and showed us how do customers use these same methods and processes to make sure that they're driving risk when they're picking vendors that are going to be developing software for them. And how do you take metrics and manage programs once they're underway, and then close the loop at the end where you measure the performance and how things actually happen. So just a wonderful set of presentations. I want to build on that. And what I am planning on doing, since this is our 40th anniversary, is I want to take you back to the very beginning. So I want to take you back 40 years and show you how this whole thing, or as Lenny said, how this magic algorithm got developed. What was the happenstance or the circumstances, the pain that Larry Sr. ran into that got him thinking about coming up with some good solutions in this space? What was the data that he was working with, and how did he develop the initial set of algorithms that we're still in many cases using today? So, and then, as Joe talked about, that these things stand the test of time, let's take some of what he learned 40 years ago and let's pull out some data sets and look at how those data sets, let's say over a decade at a time, over 40 years, how does that data compare to the behavior that he discovered 40 years ago? Is it still relevant today and with current technologies and methodologies? So that's what we'll be talking about over the next 40 minutes or so. Just for a lot of customers here that know QSM very well. There might be some people that don't know us very well. Again, it's our 40th anniversary. Larry started the company back in 1978. I'm speaking to you from McLean, Virginia, just outside of Washington, D.C., but we've got a number of offices spread around different parts of the U.S. and Europe. One of the things that all the other speakers have talked about and that we feel very important about is that these solutions should be empirically based on facts and data. So QSM has continued to collect data over 40 years, and we've currently compiled a database of over 13,000 projects. You name it, we've probably got a sample of it in there. And we use that data in our ongoing, research and development. We update it and refresh it in our tools. So if our customers are using the built-in databases, they're using the most recent set of data in the different application domains. And the other thing I think we bring to the table is we've got a lot of experience working with a very diverse set of customers, as you've seen today from the different customers that you've been listening to. And we bring that back in our research and also in our solutions that we develop for our clients. So, what's our mission? Well, it's pretty simple. It's to help our customers negotiate, make well-informed decisions, fact-based decisions, and execute successful software development and deployment. We hope that by helping them analyze some of their performance data, they can see where they can optimize their efficiencies, both in their operations and their development activities, and ultimately improve their productivity and quality over time. And again, you've heard some of the speakers today talk about how they do that and use that empirical data as the basis for that. So I won't get into the rest of this, but we're a tools company. Everybody's been talking about the slim software solutions, but we also do training and education, and we provide consulting services in this whole measurement and estimation area as well. So I'm going to take you back, but I'm also going to do that by telling you some stories. It'll hopefully make this a little more entertaining and set the context for sort of how our founder, Larry Putnam Sr., my father, started this whole thing, both the technology that he developed and the company that he started. So Larry Sr. wasn't a software guy. He was a career Army officer. So he went to the U.S. Military Academy at West Point, graduated in 1952, went into the armor branch of the Army. So they shipped him over to Germany, and he was driving tanks, around the German countryside. Later, he went and got an advanced engineering and physics degree at the Naval Postgraduate School sometime in the 60s. And that landed him a new job within the military, where he became, at that time, what they described as a nuclear effects engineer. So his job was to try and understand, this is during the Cold War, so try and understand the physics of nuclear explosions so that we could use that information to protect our troops on the battlefield. At that time, there was no personal computers or hand calculators or smartphones or anything. So he was doing a lot of these very tedious calculations on a slide rule. So if any of you don't know what a slide rule is, you can Google it, but what you'll see is that it's a very tedious and error-prone way to do these complicated, complex calculations. So at about that time, he was stationed at Sandia Base, and they had just brought in the latest and greatest, mainframe computer that there was available at the time, and they had some excess capacity. So they were offering Fortran programming courses that some of the people could take on their lunch hour. So my father saw this as a great opportunity to offload a lot of these manual slide rule-based calculations and let the computer do the work. So he signed up, took his programming course. He'd always joke that he had a little trouble getting his job control cards in the right order, but he finally got his program to compile and run and got his calculations done. And probably the most significant thing that came out of this was he got a little certificate of completion from this programming course, which he, being a good, dutiful officer, sent in to be put in his personnel file. So a number of years later, when it became time for him to do some duty at the Pentagon here in Washington, D.C., they open up his personnel file and they look at what his capabilities are, and they say, well, Larry, we don't need any nuclear guys right now, but we see that you're eminently qualified in data processing due to your Fortran programming experience. Come and run the Army's data processing budgeting operation. So he's a lieutenant colonel at this point. So he comes down, no background really in software whatsoever, and the first time that he had to sit down and justify their data processing budgets in front of a congressional budget analyst, this budget analyst had some hard questions specifically about this one program. It was called SIDPERS. It was a large Army personnel system. I think it stood for Standard Installation Data Processing Personnel System, something like that. The military loves acronyms. But the system had been developed over 4 years, and They were projecting that they needed $2 million for the next 5 fiscal years to maintain this system. And so the budget analyst was asking them, okay, well, this thing is fielded, it's operational, it's out there doing its job. What do you have to do? What does maintain mean? Well, my father's sort of new to this area, so he kind of was relying on his experts that came in with him. Nobody had any good answers. So they had a lot of technical jargon that they were throwing around, but nothing that this budget analyst could understand. So he finally said, okay, we're going to adjourn this meeting and go back to your office, talk to some of your vendors, but I'm going to need some better answers to be able to approve, these budget items. Otherwise, I got to take $10 million out of your budget. So they went back, again, talked to their vendors, didn't get really any better answers. So by 9 o'clock the next morning, he had lost $10 million out of the Army's data processing budget, which he had to spread, across all the programs that they had going on at that time. So he wasn't a very popular guy, as you can probably imagine. And that was the pain, as Lenny said, that was the pain that got him thinking about, how can we do a better job of managing these software projects? And, coming at it from sort of an engineering standpoint, he kind of understood that there's got to be more than gut feel to this thing. We've got to have some quantitative facts and numbers that we can do this with. So just by accident, he happened to be down in the bookstore at the Pentagon, and on the used book counter, he saw a book by Peter Norton, IBM Poughkeepsie Lab, 79 cents, softcover book. And there was a chapter on managing R&D projects, research and development projects. And then when he read it, he saw that they were using these Rayleigh distributions as a way to optimize the way that they ramped people and resources onto these projects to some peak level. And then they had these long tails as they sort of ramped down on the back end. So he went back and immediately started pulling some of the budget data out that they had on some of their Army programs that were underway, and he noticed that they exhibited their spending profiles, their cash flow profiles, exhibited the same sort of Rayleigh type distribution. So just by doing some basic curve fitting to some of their existing programs, they were very quickly able to get them under financial control. Now, the next step, obviously, was to figure out how can we come up with some way to do this up front, early on before, we started the project. How can we estimate how long they should take and how much they should cost? So that was the beginning of him developing the software lifecycle model, or the SLIM model. So, he started looking for some, artifacts and data. I'm going to show that to you in just a second. Luckily, he was able to find like 19 pieces of historic data on Army programs that became the basis for his modeling activities. Now, he retired back in 2007 from his official post as president of QSM. But after he did that, he asked if I'd come over and help him. He wanted to clean out some of his old files in his office, I guess, to make room for his golf clubs and his fly fishing gear. So we're pulling out all these old files and banker boxes, and in the very back, of one of the closets, there was a banker's box, and it was labeled original research. So I pulled that out and opened it up, and there were some file folders in there. When I looked at the file folders, there were a whole bunch of these acetate slides. So for many of you, prior to PowerPoint and projectors, the way that you presented your material was you did it on paper, you put it into a Xerox machine, and you copied it onto a transparent acetate, which you then put on an overhead projector and blasted up on the wall. So these were his early presentations that he had put together on his original research. So all these files and things were going to go to the recycling center. I said, no, we're going to preserve this stuff. So what I did is took and scanned that in, and I'm going to take you through and show you some of those original artifacts that'll give you a firsthand view of how he put this together in the first place and what he had to work with. So, like I said, this SIDPERS project, this was right around 1975. This was the project that caused him, the grief and pain that got him thinking about how do we do this stuff better. So let's take a look at that project. So here's the slide, SIDPERS. I'm just graphing it up, or he was graphing it up. On the vertical axis, we've got man years of effort, and on the horizontal axis, we've got the years, the time schedule. And the little blue line that you see here in the 1975 timeframe, that was the end of the development portion of this project. So you can see the little, dotted line are, the actual staffing up to, that 1975 point in time. And then the straight line dots that go on after that is what they were requesting for the budget that they wanted to support this system or maintain it. So if we superimpose a Rayleigh distribution on those actuals and their projections, you can see that it matches pretty good up until the point where they get to that delivery point where it was starting to come down in resources, and the Rayleigh distribution indicates that it should have continued to come down. And this is what intuitively that budget analyst was thinking. Why are we having a level of effort of resources when this thing is out there and operational? I'm sure you need some to fix residual defects and things like that, but it's not a level of effort for 5 years. So that was very perceptive of that analyst, and what was really probably going on here is underneath that level of effort, there was a series of enhancements, activities that would be going on along with the basic maintenance of defect correction and things like that. But that would have been represented in this Rayleigh model as a series of separate sort of Rayleigh distributions for those enhancement releases. So, that's just for nomenclature. K is what he used for effort. So this was 778 person years of effort, and it was for TD is what he used for the development time, which was 4 years in this case. So, that was SIDPERS. That was the project that lost him the $10 million. So again, when he was trying to build the model for looking forward, how do we do this earlier, he needed some data. And he was able to come across 19 projects from the Army's Computer Systems Command. So these are the projects that he had. He says he was really lucky because these were all very consistent projects. They were very homogeneous in terms of they came from the same organization. They were all, at that time they called them data processing applications. Today we call them business or IT applications. They had the same tooling environment, and they were complete. So he had the effort in terms of man years. He had the development time in terms of years. Notice how crude the data is. Today we want everything in man hours and man minutes and down to the days and weeks. So back then he's working in years and man years. And then he had 3 sort of size and scope artifacts for each one of these. He had the number of files, the number of reports, and the number of application programs. So those are 3 of the core metrics that are critical to using this model. So it was very lucky that he had that information or was able to get it on these 19 projects. So the next thing he started doing was looking for relationships between the effort and the time to those different size metrics. And he tried out a number of different correlations. So these are some of the functions that he was exploring. He had to use matrix math because he had 2 simultaneous equations that he was trying to solve for. I won't get into that. It's probably a little above my head. But the net result of that is he came up with a number of early modeling equations, and he was able to assess the goodness of fit, how good those tended to predict the actuals. So the thing here is he needed to see how well these things would intersect with one another, and that would tell him whether he had a decent model that he'd be able to pursue going forward. So here is a little manual graph. Again, he's probably doing this with a straight edge where he's got a graph log. So vertical dimension is effort in person years or man years. On the horizontal axis, he's got the development time. And here he's plotted up all of these different functions. And we can see where they intersect at the, the time and the effort point for SIDPERS. This is the SIDPERS example. And we can see that he got a pretty good intersection there. And the two that stand out are this one here that I'm pointing to on the right. That's an early version of what we call the software production equation today. And you'll notice he's got some exponents on there. In fact, it's pretty close to what we currently use. I mean, there's been some minor tweaks, but in the broader scheme of things, that's pretty much what we're using today. One of the magic algorithms that we're using, that we still use today, that stood the test of time. And then the other equation was this. He used G at the time, where it was called a gradient level, but what it really related to was how quickly you could ramp staffing onto a project. We call it a manpower or staff buildup index today. And it's, those two equations that really become the basis for what we use in SLIM to be able to predict the schedule and the effort or cost for a project based on a certain amount of scope and at a certain efficiency. The other thing that he had for a subset of those projects was he had some schedule checkpoints along the way. So not just the overall duration, but he had the percentage of the development time when they would have hit, say, a design certification, when the design would have been done pretty much, and when the product would have most of the subsystem integrated and be ready for a systems integration test. And then there were a couple of further, performance extension testing and final regression testing points along the way. So he was able to figure out not only, what's the overall time frame, but now we can start to lay in some checkpoints along that time where we can see, are we, getting the design pretty much finished up at the point in time when we need to, and are we getting to the point where everything's integrated and ready for test? So it was a further refinement that he was able to make to the SLIM model. So this was, the net result of that. Based on, a certain scope and a certain efficiency, we're able to generate a timeline and a series of these Rayleigh curves, the effort, and then use the Rayleigh curves to spread that effort over time and come up with some intermediate checkpoints that would let us know, are we tracking to this estimate, and how well are we doing to it? So that was the genesis of what we call the Putnam-Norden-Rayleigh model. That's now documented. There's a number of books and a number of people have referenced it. If you want to go in and actually look at a little cleaner, more modernized version of the math, and those are available up on our website. So, some of the key thoughts is that, we found that the Rayleigh model tended to be a good representation of how humans solve design problems, or the demand for resources or people on human, design problem solving. He also discovered, you notice that we had those exponents on the time and the effort, 4/3 and 1/3 terms. So he discovered this time-effort trade-off relationship, which I'm going to go into a bit more detail, but it's very powerful. And in fact, it's being leveraged better today than it was in those early years, because there's tremendous economics, and it's a management decision that we can make today on how we're going to resource a project, and it has a big impact on the cost and not as big of an impact on the schedule. And we'll look at some data. The other thing that we think he discovered is, even though we call it a software production equation, what we really think it's modeling is how humans, again, solve complicated design problems, and we can apply it to other design domains. So we've looked at it in hardware, firmware, infrastructure projects. If you think of all of those things, all of those projects, they take time. They take some application of people over that time or effort, but what you have to adapt is the size metric. So in firmware, you're probably talking more things like, logic gates. In infrastructure, you're talking things like, hardware, servers, networking, software installations, configurations, all that kind of stuff. And in hardware, you're talking hardware components. So again, we think what he discovered fundamentally was a nice model for how humans go about solving design processes. So, two very nonlinear things, that he discovered, that one is that as the size of the systems change and as they grow, there's a very nonlinear change in the amount of time that it takes to deliver them and the amount of effort that it takes. And the other thing that he discovered, and again, I'll go back to some of the earlier presentations today, so that builds the case that until you know something about the size and scope of what you're trying to do, you can't have a schedule and you can't have an effort because it's so dependent on the size and the scope. The other thing was that time-effort trade-off, and really what it models is the communication complexity on a team. So as we add people to a team, we increase the communication paths and we increase the communication complexity. And the more communication paths that we have, the more chances for miscommunication, and in software, that shows up as defects in the software. And again, it's very nonlinear. You've got these different exponents on the effort and the schedule terms. And so it's really showing us a function that it's, using big teams is a very expensive way to get schedule compression, and in fact it also has a negative impact on the quality. But if we can go the other direction, we can actually get a positive. We can use those economics in a beneficial way. So just to sort of show that with data, this would be a fairly contemporary look at the QSM database. So if I pulled out a recent sample of projects, and I'm not getting very fancy here. I'm just pulling out everything, not really breaking it out by application complexity. And I'm plotting it up. We've got some management term in the vertical dimension. So the upper left is calendar months versus size. And I'm using implementation units. Over on the upper right, I've got person months of effort. And in the lower left, I've got defects. And it's hard to see on the slide, but I'm compressing the data down with these log-log scales. So if I just did a regression fit through that data set and then put those curves on a set of linear axes, that's what you would see down in the lower right-hand corner. That down in the small to medium size regime, that small changes in size have a big impact on the duration, but not so big of an impact on the effort and the defects. So if that's where we're living in that small to medium size regime, then if we take on, say, a little bit, an additional couple features, we can go from having a decent probability of meeting our timeline to having a very low probability because it has such an impact on us. But if we're building very big systems, like some of the ones that Joe was referencing, dimers, things like that, then if we get additional scope creep, it has a much bigger impact on the cost and on the quality of the system. So again, this is one of the nonlinear things that Larry discovered. We'll take a look at it. It's still alive and well today, and I think a number of our speakers have alluded to it by how important it is to get a handle on size and scope, because before you can do that, there's no way to come up with an effort or a schedule for a given set of capabilities. And then this was the other thing that he discovered, this time-effort trade-off relationship. So given a certain amount of scope and given a certain capability or productivity that we're operating at today, it really defines this function. So no one way to go about a software project. We can, use a large team and try and move back to the left. And what happens is, as I add more and more people, I get diminishing returns on the schedule compression, but the effort and the cost just continues to skyrocket. And you get to some point where, you just can't, you get to some impossible zone where you either can't get the resources, it becomes cost prohibitive, whatever. So we kind of define that as sort of the impossible zone. The other direction, and this is, we used to take a lot of heat on this in the early days. If you go the other direction and you take a little bit more time, you can bring the effort way down, and you can take that to an extreme as well. Well, if I double the schedule, then I can do this project for free. But what you run into there is there's certain limits on how much you can do that. You either start dropping the team down to an unreasonably small number of people, you'd say 3 people or less, where you're not going to have the necessary skills or any backup or contingency and resources if you need to, or you get to some point where there's just some date where we can't go beyond. It's either mandated, regulated, or for a commercial company, it's a market window that we've got to try and meet. So there's some, part of that curve that we call the impractical region. That's just not, we're not going to try and plan there. And usually what happens is you've got some constraints that limit that trade-off region to some smaller finite zone. It might be a maximum budget, it might be a maximum time frame, and although I'm not showing it up here, it might be implied reliability that you need for the system. So, those were the two things that he discovered. He was he was trying to socialize this model with some of his colleagues in the military, and he was talking with some of the, I think it was Hanscom Air Force Base, he was talking with some of his colleagues in the Air Force, and they made him aware of an additional data set that was out there. It was some data that was being collected by the Rome Air Development Center. I think it was up in upstate New York. And he was able to get access to that data. So there were 180 projects, a much larger data set. There were multiple organizations in there, so it gave him the ability to see, does this model work in a more diverse environment, whereas the first 19 projects were all in the same organization. And he had a whole bunch of different types of projects from an application complexity standpoint. So there was some business stuff in there, but there was also engineering class software, so that's command and control, scientific system software, communications, and there was also real-time and weapon systems in there as well, so firmware and real-time application code. And because it was a very diverse data set, they had a much broader size range for him to test, and there were a lot of different languages in there. So it kind of gave him a nice way that he could broaden out the validation of his model with a much larger, more diverse data set. And guess what he discovered? He saw exactly the same behavior in that data in terms of a nonlinear scale up in the schedule and the effort as the size increased, and he saw that very same trade-off relationship in all those different types of systems. So again, a very nice way that he could validate this with an additional set of data. So what I thought I'd do now is let's go, we've published a number of research reports, and where I've got them, I'll put the URLs in there. And these are freely available. You can go up to the research part of our website and pull them down if you want to get the more details on how we did it. But essentially what I'm going to do is go look at some of our research artifacts where we revalidate these relationships, specifically the trade-off relationship, every decade. So we'll look at some data from the mid-90s, and we'll go and look at some data from the mid-2000s, and we'll look at some data that we've collected recently, and we'll see how well does that trade-off relationship hold up with those different data sets. So let's do that. So this was an article that was published. It was actually published by my brother, Doug Putnam, in the mid-90s. And it was called Haste Mace Waste. And it was all about showing that, if you try and compress the schedule too much, you're very wasteful on resources. So he pulled out a set of projects. I think these were mostly business systems at the time. And he split them up into two groups. A large team. At this point, I think he was using 32 or more people, or excuse me, no, it was 20 or more people for the large team approach, and 5 or less for the small team approach. So he took the sample of projects and broke them out into ones that had 20 or more people or 5 or less. And then looked at, he picked a size point. I think he used the average size from the data set. And then looked at what would be the difference in the average effort, number of defects that would have been created, and the schedule. So you can see, from the effort standpoint, at that average size point, if you used a small team, you could build that amount of functionality in, 25 person months of effort. And if you used a large team, you were going to be using more like 178 person months. So what is that? 4 or 5 times more effort for the same amount of functionality. You would have generated on average 33 defects for the small team approach versus 170 defects using the larger team approach. And then when we look at the regression fits for schedule, we see that there's almost no difference a fractional part of a month different in the schedule, about 9 months. So pretty impressive here that, there's a tremendous amount of leverage by optimizing your uses of resources and not being wasteful. And if schedule, is what you're concerned about, there's very little impact on the schedule from using a small team. This, by the way, this article still gets a ton of traffic. It gets referenced by a lot of people in the Agile community who are trying to back up and justify their advocacy for using small functional teams. All right, let's flash forward to the mid-2000s. So again, this is actually published in the first almanac that we put out, which was in 2006. So our almanacs are collections of research articles that we compile and put together and put out there for the industry. They're freely available. You can download them in a PDF format on our website, so that's the URL. And again, went and pulled out some projects, tried to use the same breakpoints. Projects, these are very recent at this time, IT projects, ones that were developed with 20 or more, ones that were developed with 5 or less. And again, what you see there is a 4-to-1 ratio in the amount of effort that was expended at a given size. In this particular case, it was a 6-to-1 difference in the number of defects that were created using a large team versus a small team, and virtually no difference in the duration between those different resourcing approaches. So again, another validation that this behavior is alive and well, in the new millennium. In the latest almanac that we've just published, 2017, more data obviously, and again, you see, I'm not going to belabor it, but you see exactly the same behavior. A lot of divergence in the amount of effort in the regression fits, almost no overlap in the number of defects, and, large amount of overlap and virtually no difference in the schedule in the recent data. So I wanted this to take a step further because I know today Agile development methods are popular, so I went to Kate Armel, who manages our database. She's going to be actually, along with Laura Zuberg, doing the next presentation. I said, Kate, can you pull me out a sample of projects that used Agile methods? They're fairly recent. So she went in and pulled out a sample of 436 projects for me. They had a pretty broad size regime, anywhere from very, very small to, some pretty big systems. And, the median average staffing was, just shy of 5.5 people, and the mean was around 9 people from that data set. So what I did is I looked at the data, and I sort of wanted to use a sample from within a size regime where, I had a good sample of data, but I didn't have a lot of, say, flaky outliers on the fringe. So I used a size range of, 1,000 implementation units up to 200,000, and I had a nice set of data, number of projects. For the large team, in this case, because everybody seems to be using smaller and smaller teams, and I think these were primarily business or IT projects, I used greater than or equal to 9 people for the large team approach, and less than or equal to 4 for the small team approach. Notice that I've got, over 100 projects in each of those samples, so I've got a decent sample size. And here's kind of what it all looks like. And again, you'll see a very similar pattern: large team, small team, big difference in the effort, regression fits. I'll show this to you and get you some numbers. Difference in the number of defects that are created, not a lot of difference in the schedule. So let's look at those individually where you can actually see some of the numbers. So this is person hours of effort, okay? So I've got the graph up above with the average regression fit. So red is large team, blue is small team. And then down below I've got a table which actually gives you some numbers, and I think what it does is it goes in at size quartiles. So at roughly 2,500 IUs, it'll read off the average there. So at that size, if I used a small team, I would expend around 778 person hours of effort. If I used a large team, I'd be closer to 2,900 hours of effort. If I'm somewhere in the middle, say 23,000 I use, small team, 1,700 person hours versus 9,300 using the large team. And if I'm on the high end of things, then 3,500 hours versus 27,000 hours. So 4 to 8 times more effort is expended depending on whether you used a small team or a large team. Let's look at duration, schedule, okay? So again, down on the small end of things, it would have taken a little over a month using a large team, a little over 2 months using a small team, so, about a month or less of schedule difference on that. Up on the high end of things, you can see big systems, it might have taken 7.5 months, 7.59 months versus 7.66 months, virtually identical schedule up on the large end of things. So pretty much less than a month of difference in duration, but a huge difference in the effort. And let's look at the defects now. So again, when you look at the number of defects that were created on average using the large team versus the small team, 3 to 4 times. Again, very similar to what we were seeing in those previous days. That's 3 to 4 times more defects are created using the large team approach to software development. So one of the things that has been very, very encouraging to me and the rest of the folks here at QSM, especially the ones that have been around like me for 30 years, that trade-off relationship that I showed you, when Larry first came out with that was very controversial. Nobody would ever believe it. And in many cases, that's because everybody in those early days was going for maximum schedule compression at any cost. What we're seeing with modern Agile and Lean development methods is they fully embrace using smaller teams, and keeping scope small. So they fully embrace these concepts, and guess what? That the positive economics work for them, okay? So, small cross-functional teams, I'll show you some examples of rules of thumb that they use on how they do their staffing. The other thing Agile methods do is it puts an emphasis on size measurement. As one of my colleagues says, among the 5 core metrics, it makes size a first-class citizen. It's very important to measure it. And we saw some that use epics and user stories and story points. Because size is such a critical driver to how long projects are going to take and what they're going to cost, and even the quality, how many defects we're going to have to generate and find and fix. It recognizes that change is inevitable, so this emphasis on constantly grooming the backlog and putting emphasis also on if it's not valuable, don't put it in. What does that do? It keeps the size as small as possible. Again, making those economics work for you. And then the other thing is that they deliberately plan in short cycle times. Again, that helps to reduce change and churn. They strive for continuous delivery, and the only caveat I'll put in here is there's going to be some minimum viable product or some minimum marketable features, whatever you want to call it. So it's important to figure out what is the size and scope that maps to the customer's, minimum viable product, because that's what's going to determine the minimum duration and the minimum cost. And then, obviously we can add things on after that, but this is what's going to determine the minimum delivery point based on the value and the functionality. Again, this is some research that we did back in the 90s time frame, where we looked at different team sizes. I think this was looking at what's the optimum team size. And what we found out was, 5 to 7 people, teams with 5 to 7 people had the smallest amount of variation in productivity. I was looking around for, in the Agile world, things that would kind of what they were advocating, and in the Scrum guide, surprise, surprise, I found the guidance here on development team size. Shouldn't be smaller than 3 people. Again, you need the backup and the skills to bring the project off, but we don't want to have any more than 9 people on the project. So again, maps very nicely to that empirical data that we were looking at, back in the 90s. The 2 pizza rule. This was a concept that was developed by Jeff Bezos. It was developed to keep meetings small. I don't think he was a big fan of meetings. And the concept here is if your team or the people in the meeting is bigger than you can feed with 2 pizzas, it's too large. But the science behind it exactly matches what we see in software. It's because as we, add people, if we go from a team of 6, which you can feed 2 pizzas with, to 12, to 24, you get this exponential increase in communication paths. And again, as we've already talked about, as that communication complexity increases, we've already seen in the data has a huge impact on the cost. Doesn't impact the schedule so much, and we generate a lot more defects. So, so 2 pizza rule, applies just as well in software as it does to, your keeping your meetings small. And then this was just another trend that I put together, or actually Kate put this together for me. I just wanted to look at trends in size of projects. So she gave me the average size and implementation units, from, way back in the early 70s to today. And you can see that there's been a very, very pronounced trend as we've moved forward in time that the average size of systems have been coming down. I think early on, what you're probably seeing was that was maybe more driven by technology and more powerful languages, going from lower level languages, assembler and things like that, to higher order languages like COBOL and Fortran. But I think more recently, it's being driven less by language technology and more by a concerted effort to keep the project small because of the economics that work for you and because it reduces the impact of change. And I think you're also seeing impacts of reuse. People are building reusable software, so that reduces the amount of new software that they have to develop. So just, thought that was interesting and shows how the average size of projects have been coming down over, 4 decades. So, I'm getting close to the end of my time slot. I think what I've tried to show here is how Larry's original research on some of those ugly acetate slides are still relevant today as they were 40 years ago. So that obviously we've had to enhance and adapt, some of the things around the basic model, like not everybody uses Rayleigh distributions anymore to staff their projects, as Dan showed, and with some of their Agile templates, a lot of times they use fixed teams, so we've had to adapt things where you can basically pick the shape and the geometry of your resource profile. We saw the current Agile data, again, has that same nonlinear trade-off that we saw in the early data and the data over the 4 decades. And again, the thing that we're really excited about is, after 40 years, the industry has caught on and is doing things smart, like using small teams and keeping the scope as small as possible, because that exploits all the positive economics. And it's nice to see that, because I can tell you when I first got into this business, trying to sell people on that, they wouldn't even listen to you. So that's a good thing. So with that, I think I've got 10 minutes left. I'm happy to open it up and answer any questions that you might have.
Thanks, Larry. I think we've already got a couple of questions for you. I know they haven't changed much, but how have the formulas changed or been adjusted over time?
So if you think of the formulas, they're I'm trying to think of a good, they're parameterized. So what we're able to do is that productivity index is one of the key drivers. So by refreshing those industry databases that we've built into the tools, we're essentially modifying those equations with the more current data and the more current PI. So we're not having to modify the equation, let's say, but because it's parameterized through that productivity index, by being able to refresh it with more recent data, and more importantly, as you've seen from some of the clients here, using your own data adapts that model to the way you do things. That's built into that productivity index. But we've done some things. I think the reliability model, we've gone back and refit that. There's a reliability model that's built in that'll estimate the number of defects. We went back and looked at that and noticed that we needed to tweak that a little bit, so we made some adjustments there. to some of the parameters in the reliability model. But fundamentally, like I said, if you go get a copy of Larry's book or pull down some of the papers that talk about the software equation, fundamentally those exponents, 4/3, 1/3, haven't changed. That the core estimating algorithm is fundamentally the same.
Outside of team size, is there any data to answer questions about whether Scrum or Agile teams achieve a higher productivity index than traditional projects?
Yeah, we did some research. In fact, I published, there's a number of them. You can go up on our website and look at them. And what we were seeing was early on, I'm trying to think the time frame. I think I was doing this in the mid-2000s. But what we were seeing was some of the early adopters. And a lot of these companies, they were sort of boutique type of firms. So some of the early adopters, when we got some of the data from those projects, we saw, yeah, there was a market increase in productivity and quality on those projects. And again, we saw another thing was that they were using smaller teams. So they had both higher productivity and smaller teams. And then we followed that up with later on as we started to get a larger and larger sample of Agile projects where it was now being adopted by larger enterprises or trying to spread it out in a bigger way. And we didn't see as big of a difference, in those projects. So it might have either been because of, their level of rigor and how they had, adopted the Agile methods. Again, in the larger data set in the big enterprise systems, Fortune 500 companies that were doing it, we weren't seeing that they were, sticking to the small team approach as much. They were resourcing it more the way they had traditionally resourced things. So they were essentially not reaping some of the benefits that we saw from some of the early adopter projects. So yeah, if you go up on our website or Pulse Elizabeth, we'll be happy to send you out some links. You can go look at those. I think if you go on my LinkedIn profile, there might be some links to those specific articles as well. So we've done the research, and again, it's not definitive, but within the context of if they were using the principles in a pure way and doing things right, you did see the benefits when as they got adopted by bigger organizations, and it started to be less definitive at that point.
What reasons do you attribute to the current trends in project scope and team staffing?
Well, I think I've talked about some of them. The Agile and Lean community definitely promotes, and has I think team members, I've learned this over 30 some odd years, the people down at the team level inherently know, what's the right skill mix that I need and what's the right number of people that I need to do this. Unfortunately, management, the one thing they have under their control is if they feel like a project is behind schedule, they'll throw people at it because that's what they have under the control. So now that Agile methods are being driven more at the team level, we're seeing smaller teams in the data, especially when they're using Agile methods. And again, you saw the data, the size of the systems is coming down, and I think, again, there's this notion that try and keep things small. If it doesn't add value, bells and whistles, things of that nature, don't put it in. Because modern development methods recognize that the customer doesn't always know what he wants, or he's going to change his mind, so let's build that into the methodology. So this constant reprioritization and grooming of backlogs, I think, is wonderful because it allows for that pivot and change. What's important is if we've got some fixed time box that we have to deliver within, and we've got a fixed team over that time box, what's more important is knowing how much scope can we fit within that. And as we reprioritize, we need to make sure that we keep the scope within those limits if we want to be able to meet those fixed duration and cost cadence points. So yeah.
Is it possible to measure the benefits of implementing Agile methods to build a business case to show management the return on their investment in Agile transformation?
Yeah, absolutely. I mean, that would be more in our measurement and benchmarking areas, but sure, what you do is you come in and you get a baseline in place that, let's say, prior to implementing Agile, if we're using, let's say, more waterfall or sequential methods, and you collect up some data and generate a baseline, for the 5 core metrics. What was the functionality you delivered? How long did it take you? How much effort did you expend? How many defects did you create? And you get that baseline in place. And then, as the organization starts to transition to Agile, they get their people trained up. It's going to take a period of time. It's probably not going to be, 1, 2. It might be a year or 2 or 3 years, whatever it takes to fully implement Agile methods. And then you measure those projects that are delivered using the new methodology, and you fit those trends. And I didn't talk a lot about. We've got a metric that we use, which is called a productivity index, which is a measure of efficiency, and you compare the two and see, are we getting our cycle times down? Are we, lowering the amount of effort that we spend on projects? Are we improving our quality? Is our productivity changing over time? And in many cases, you'll see that it does. And then what you have to do is build a business case and say, okay, well, what is that worth to the organization in terms of a return on investment? Getting our systems to market faster? Are we more competitive? And all those types of things. What about the quality? So taking, the delta between those different baselines and putting that in business terms, which the senior guys understand, which is, ROI, return on investment, faster to market, better quality, more satisfied customers. That's what you use to sell almost any type of improvement initiative, whether it's Agile or otherwise.